Hello world, here's Jorge and let's continue learning about object detection in PyTorch. In the last video, we defined the gradients, the horizontal and vertical gradients, both for grayscale channels and so in this case, RGB channels. But before continuing with the task of defining HOG, let's modify a certain aspect of this code, because if we have a look at the horizontal and vertical gradients, there's something that is implicit in here. That is that the group is equal to 1, because by default, so if we look at the PyTorch documentation, if we look at conv PyTorch, by default, groups is equal to 1. So here we didn't specify anything. So essentially what this means is that it's going to be, so groups is going to be equal to 1. But we don't want that. What we want is having groups is equal to 3. Why? Because we want to have an output channel per input channel. We want to have a one-to-one mapping. Okay? So if we set here group is equal to 3, we're going to have just that. Okay, so given that now we have one channel per group, we need to modify as well the expansion of the RGB gradients. Okay, and how? Well, we need to remember, actually let's write this down, that the structure so the meaning of these numbers essentially, and hence of these as well. Yeah, so essentially what these mean are the following. So the first element is actually the output channel in this case, so out channel. The second element is going to be input channel over the group. Okay, and then we also have the other two elements that are going to be the kernel height, and the last element is of course the kernel width. Okay, great. So in that way, now we understand that well, the out channel still going to be in this case 3. Okay, because we have 3 color channels as an output, but as an input, as we are dividing the input channel, which is equal to 3 too, by the number of groups that we just said we're going to set to 3, hence this is going to be 1 instead. Okay, so in that way definitely we can correct that aspect. Okay, but now let's have some more insights on how essentially reshape and expand work. Okay, because that's going to be beneficial for later as well. Yeah, so let's start importing torch, and also import torch.nnsnn. Great. Well, let's first go here. Let's actually redefine, for the sake of completeness, what the gradient filter D was. So essentially, these was the hard coding of the gradient weights, okay, for the scaling gradients. Okay, so we said that D was equal to torch dot tensor, and we had -1, 0, and 1, because we were taking actually the difference between neighboring pixels, only the two like closest to the reference pixel. Okay, and then we had the D-type, which is for PyTorch tensors always going to be float 32. Again, this is done by default, but for the sake of completeness, let's put it like that. And of course, we need to divide this by 2. Okay, great. Well, what is this giving us? let's find out. So basically, we're going to have, let's put here space for later, and well, we're going to have this tensor, okay? But a good question would be this tensor, what it's the shape that it has, right? So it looks like one could say, okay, there are 3 elements, so why not saying that it's 1 by 3? Well, not really, because this is actually a 1D tensor with 3 elements on it, which needs to be say distinguished from the tensor that has 1 row and 3 columns. Okay, but we'll see how it works. So essentially here we have a tensor that is of a shape 1, okay, and we're gonna actually verify that. So have a look at it. Exactly, we have a tensor that is 1D and it has 3 elements, okay, embedded in it. Okay, great. So now we actually want to have a look at the, actually let's put here shape for later so that we actually visualize it. Okay, but this is the let's specify this here. This is the weights, so handcrafted weights for spatial gradients. Okay, great. But now let's actually have a look at the gradients or the weights of the color channel, or like the RGB gradient, horizontal gradient. Okay, RGB horizontal gradient. So we actually defined it above. We said that the horizontal RGB gradient was equal to the following. Okay, now corrected with the assigned groups, like 3 assigned groups. Okay, all right, so we have it there, and now let's actually see the say weights that are associated to it, because PyTorch by default so is going to compute for you the weights, right? So let's have a look at them. So it would be let's say now that we want to find out the RGB PyTorch weights. So how do we do that? Well, we simply extract the weights from the actual gradient. Okay, and let's have a look at them. And here we have them. Okay, let's have a look. Okay, great. So we have here 1 vector per essentially color channel, and yeah, let's for the sake of comparison, let's just have a look at the explicit values again. You see here we have the handcrafted values for the weights, and here we have the PyTorch weight values. Okay, of course they don't match, so what we need to do is to replace the handcrafted, the ones that we want to implement, and basically get rid of the PyTorch weights in this case. Okay, so essentially what we want to do now is just that. Now, and but what is the problem? Because we could say, okay, we explained the last video, let's just equalize both and that's it, and that's how we assign, right? But what is the problem? The problem is that the shape is not the same. So of course, if we have a look at it explicitly by calling shape, exactly, this is what we get. We get for the handcrafted we have 3, while for the default, for the PyTorch computation, we have a 4D tensor. Okay, so we need to modify the handcrafted shape. Okay, and how do we do that? Well, we first of all need to get, so obtain, or better say shape, the handcrafted to be 4D. So let's shape our original tensor to be 4D, the handcrafted tensor. Okay, and how do we do that? Well, we do that with reshape. Okay, and essentially let's actually start with that. So we just say d.reshape. And how does reshape work? Well, so essentially, as we introduced in the last video, what we need to do now is just to say, for example, here we have these 3. Okay, these 3 elements, we want to keep them. Okay, it's just that we want to reshape the tensor. That's it. But the information that contains, we need to carry on with it. So now what we do is to actually place these 3 elements in the last position, which is going to imply that we're going to have 3 columns now of our tensor containing these 3 elements. Okay, so how do we do that? Well, what we need to do now is just to state that we simply want to reshape our tensor in the sense that we want to we're adding 3 dimensions now. We're adding 3 dimensions, and we are keeping the original, say, dimension, the 1D dimension, we're keeping it, and the elements within it, we also are keeping it. Basically, we're keeping that information too. So how do we specify that we want to keep that information? So that is done with -1. Okay, with -1 we keep that information, right? Great. So now let's just have a look at it. Okay, great. So you see, let's just for a second get rid of the shape in order to compare. So you see, we have exactly the same information than in the original tensor, just that now the dimensions of the tensor are basically 4D. Okay, while in the original one was 1D. Okay, great. So let's just rewrite here shape, and now what we need to do is to carry on with the process. And yeah, just for the sake of comparison, let's just place here the shape 2 so that we can compare exactly. So you see, now we transformed the original handcrafted tensor into a 4D tensor, keeping the information in the last dimension slot. Okay, great. So now how do we carry on? Because our goal is to actually gain this shape, so to actually get our tensor to have this shape. So we still need to work out this. And how can we actually get 3 in the first position? So essentially what we can do is to expand the original tensor D. Okay, so now let's we expand to get the desired dimension of 3, 1, 1, 3. Okay, great. So let's do that. Let's proceed with that. So what we do is just simply use this. So we're gonna type this reshape. Okay, and expand. So that, and exactly. So in the first position, remember, is the output shape. The output shape needs to be 3 exactly, and the input shape is basically the second position is going to be in channel over the group number. So in this case, 3 over 3, 1. But of course, what happens is that yeah, this value indeed didn't change, right? So when we went from reshape to expand, this value of 1, right, is not going to change. So how do we specify this? Well, you can do either use 1, it will be okay, or just call the previous one. It's just -1, yeah. Great. So we don't change the third position either, so it's going to be a -1 too. And finally, we're going to get the last position to have these 3 elements, okay, which we don't want to change either. So again, a -1. All right, and we want to clone this because we don't want to modify the original D. Okay, great. To just have a copy with a separate copy. Okay, fantastic. So in that way, we're indeed, you see, perfect. We're gonna have 3 exact copies of the gradient filter weights. Great, 1 per color channel. That's exactly what we want. Perfect. So yeah, just to also visualize the say shape. Okay. Yeah, let's just print the same. So having exactly the same, but with the shape, because in that way we can directly verify that we get the desired shape. Great. That's fantastic. That's fantastic. So now what we want to do, well, that was just say deeper explanation on how expand, how reshape work, and also based on the correction of introducing here 3 group numbers. Okay, great. But let's continue. Let's move on. And now what we want to do is to talk about direction projection filters. Okay, so let me define that. So let's discuss direction projection DP filters. Okay, great. So the DP filters basically compute projections of image gradients, okay, onto a set of predefined orientations. Okay, so in other words, let's put it in simple words. So DP filters are a way to measure how much the gradient, not gradient, right? So how much the gradient at each pixel, points in a, say, reference direction. Okay, so points in a reference direction. And what do we mean with reference direction? Well, remember that we introduced a variable called number of orientations, okay? And this variable, what it did was to split the, say, angular space, you could say. So imagine having the whole angular space from 0 to 360, yeah? So these reference directions are going to split this space into as many parts as we set the number of orientation variable to. Okay, so in this practical, we're going to set number of orientations equal to 9. Okay, so let's highlight that. Great. So just to stress that, I essentially understand the DP filters to be like rulers, that essentially what they do is to measure how much the gradient arrows align with the reference directions. Okay, that's how I understand it. Great. So now we actually want to define the, say, weights that are going to be, say, introduced in the orientation gradients. Okay, we're going to proceed in a completely analogous way as we did with V. Okay, but just now with a different type of gradient. Okay, great. So let's do that now. So let's start by initializing. So we're going to initialize the handcrafted DF filter weights, just like we did for D, yeah, completely in a completely analogous way. So we're gonna call this orient, okay? And how are we gonna define it? So we first are going to define, say, we're going to define a tensor filled in with zeros. Okay, so let's just create zero tensor. Well, zeros. And okay, so what dimension is going to have, right? So we want to have a 4D vector, just like we've been working on with the, say, gradient filter D as well, right? So let's do that. So in the first position, we're going to have the following variable: 2 times the number of orientations, okay? And let's actually define here number of orientations as NO and set it equal to 9, okay? So first position is going to be 2 times NO, then second position is going to be just 2, and the rest just 1, okay? We'll actually dive into this in detail, don't worry. So we have it that way, and we also want to specify the type, okay? Again, is going to set it by default as 32, but just to stress the type, because as you will encounter, say, errors related to shape are one of the most frequent in machine learning, so it's really important to really get acquainted with the shape of each of our say variables and objects that we deal with. Okay, so it's going to be float 32. Okay, great. Yeah, that is going to be, say, our orient, that is the weight, okay? And actually, so what are these values referring to? Okay, that will be an interesting question to say tackle. And essentially what we're having is the following. What we're having is that this position is referring to the output channels, okay? And essentially these other number refers to the input channel, and these numbers refer to the kernel sizes. So this the kernel height, the second one the kernel width, just like we discussed with these values here. They mean essentially the same than here. Okay, great. So actually, just because we'll need to access elements of our tensor when we want to fill in the gradient weights of our DF filter, yeah. So before we do that, let's actually inspect, or let's see, or better say, let's learn deeper how can we access the elements of a tensor. Excuse me. Okay, so to do that, I have here a random tensor, completely random tensor with a shape that we're gonna run right now. We have 40 tensor, exactly, with the shape. So essentially, almost the same than here, except that instead of having, say, in the last dimension 1, we're going to have 2. Why? Because it's a bit more interesting when it comes to inspecting, or when it comes to identifying elements within tensor, to have more than one column. Okay, and when we understand how to work with 2 columns, we'll automatically know how to deal with 1 column only, okay? Because this example is harder. Great. So let's proceed and let's understand how to access elements of these a tensor of this shape, okay? Of 40 tensor, yeah. So let's first access. Okay. Let's first access batches. And when I say batches, I mean, so first batch, second batch, third batch, fourth batch. So say we want to access the first batch. How do we do it? Well, we just say random tensor. And we place here 0. Great. So in that way, we have indeed the first batch. And in a completely analogous way, we can get the rest of batches. So simply, instead of 1, we will have second batch, third batch, fourth batch. Great, indeed, what we expect. Fantastic. So now, let's say that we not only want to access a specific batch, but we also want to access a specific row within that batch, right? So let's do that. So access rows within batches. So to do that, we are simply going to do, say we want to access the first row of the first batch. So how do we do that? Well, we have this, and we will need to specify that we want the first row. So we will specify 0 here. Say we want to actually have the second row of the second batch. How will we do that? Well, what we will do is specify that we want the first or the second batch, and we want the second row. Let's see if it's working. Okay, so indeed, for the first, we get the first row in the first batch, and indeed we get the second row within the second batch, like that. Okay, great. But let's say we want to access a very specific element within the tensor, a specific element. Okay, so how do we actually select specific row? So let's type that. So select specific row column elements. Okay, so how do we do that? Well, indeed, so we can actually have a feeling already based on what we've been discussing. So say we want the second element within the first row of the first batch. Okay, so in that way we'll say, okay, the first batch, the first row, well, actually this second element, okay, specifies indeed the first row, but now what does the third specify? Well, what it specifies that is that we want to access the element within these yellow brackets. Okay, so indeed here we need a 0 because we're saying we want to access the element within the yellow brackets. Okay, and we set the second element, so we will place 1 as basically indicating that we want the second column. Okay, so now let's say we want the for example we want this element. Okay, so we want the last element, so we want the element that is placed in the second column second row of the last batch. Okay, so how do we do that? Well, simply random tensor, and here we place, well, what is the batch that we want? We want the last one, in this case, then it's going to be 3. And then we want the second row, right? So second row, and we want the element within the yellow brackets, so 0 here, and we want the element in the second column, so it's going to be 1. Let's see. Great. So as you can see, for the first batch, first row, element within the yellow brackets, and first column, we get a 9 indeed, and indeed for this one we get 6. Fantastic. So now that we understand better how to access the specific elements of a tensor in PyTorch, so now we can proceed and define. Okay, we can now start defining the handcrafted DF or DP filter weights in an analogous way to what we did for the. Okay, so for that, let's bring this down, because this is part of that. So let's actually place this here better. Great. So there we have it. We initialized it like this. Great. And now we actually want to set up a loop. Okay, we want to set up a loop in the following way. So we're going to have for I in range. Okay, and this range, what is going to be? So this range is going to cover all the possible number of orientations. Okay, so that is an O, but that is not enough. Why? Because this number of orientations we set equal to 9 by default is only taking into account the positive orientations. So for example, if we are saying that we have a number of orientations equal to 9, yeah, so we need to divide 360 by 9, yeah, that's 40. So that means that we have 0 to 40 and so on and so on. But that is only taking into account the gradients that are going to be placed in those regions that are positive. But we need also to take into account the negative value, the negative components. Yeah. So to do that, to take into account the negative, say, contributions, we need to multiply by 2. Okay. Great. So that's clear. Now we need to define the angle. Okay, we need to define the angle. Oops, yeah, I'm definitely not a robot. Okay, so we need to define an angle. And how are we going to do that? So essentially, well, what is the angle? Well, and we're going to work with radians. Okay, so 360 is 2 pi. So we're going to start with the pi. And great. Well, I think I didn't. Yeah, I didn't. So we need to import phi. So great. So we have 2 times mp .pi, and we need to divide that by the number of possible orientations, just based on the same reason that we said that we need to essentially take into account all the possible orientations, okay, both positive and negative. So in that case, we need to divide 2 by, so we need to divide by 2 times number of orientations. Great. Fantastic. And now, of course, as we're looping, we need to take into account every case. So we need to definitely multiply by I so that we get the angle that corresponds to each value within the possible orientations. Okay, great. So now what? Now what we actually going to do is to place in each row, we're going to place cosine and sine. Why? Because what we want to do with this, because remember what we're doing here is just to define in a handcrafted way the weights of our, in this case, orient gradient, okay? And these weights are going to mean the following. So when they are operated or are applied to the pixels, okay, the pixel gradients, what they are going to do are basically to take the projections of the gradients associated to each pixel. And when I mean projections, I mean when I say projections, I mean both horizontal and vertical. So for the horizontal, we are going to need to multiply by the factor of cosine, because remember, from trigonometry, of course, we know that the horizontal projection, yeah, is equal to the actual vector times the cosine. So what we are going to do is to say place here the cosine, place the sine, and hence when we apply this to the pixel, hence this vector in the analogy, we are going to multiply the vector times the say cosine and sine, and we are going to get as a result the horizontal and vertical projections respectively. Okay, very interesting. So let's do that. So how are we going to say, because right now what we have is just a bunch of zeros, okay? So what we need to do is, okay, say, look, instead of having zeros, and well, actually, just for the sake of say clarity, let's actually visualize how it looks right now. So you see exactly. So what we get is a bunch of zeros that look in the following way. And of course we have just one element because we have this shape of just 4, 2, 1, 1. Okay, as compared to this one that was 4, 2, 1, 2. Okay, great. So what we want to do is to, instead of having zeros here, so we're going to have the say horizontal, in this case we're going to be the horizontal projection component, and here the vertical projection component, and here again horizontal, vertical, horizontal, vertical. Okay, fantastic. So let's do that. So how can we do that? Well, we just learned how to access the elements of the tensor. So how do we access the rows of a tensor that has this shape or similar? So essentially what we do is to just call for the first two elements, yeah? So we say orient, well, we're going to be looping through the different batches, and what we want is in the first row of the batch, we want to place the essentially cosine factor. Okay, so we're going to have cosine, and we're going to have the angle. Great, fantastic. So that is for the horizontal term. This is the same for the vertical or the analogous. Okay, but now instead of 0, we have the second row. Great. And instead of sine, instead of cosine, we have sine. Great, great, great. That's great. And now let's just just to have a look at how it looks right now, because we had a look at by default, yeah, let's, instead of actually visualizing the whole thing because it's a bit lengthy, let's just visualize. So let's just visualize the first element, say, okay? So I just want to visualize the first column within the first batch, okay? Just as an example. And what we want to do is to compare these, because remember, this one is just actually for make it a bit clearer, like more clean, let's actually put here a string, and let's say initialize first batch first raw element. Okay, and we want to compare it with the handcrafted. So handcrafted, so initialize, well, just to make it more clear, this is a weight, yeah. Weight, so, and now handcrafted first batch first raw weight. Great. Yeah, let's have a look. Okay, great. So it turns out that you see, we get a 1 with the handcrafted. We get, of course, 0 in the initialized, as we expected, because what we actually are doing is just to replace the zeros by the handcrafted weight values. Okay, and just for, yeah, instead of visualizing the first, why not visualize? Well, of course, in the first case, we're gonna get the 0 as well. But what about this? The second one? Oh, we get a 0, which makes sense. Why? Because the first one corresponds to, yeah, of course, it corresponds to 0. So sine of 0 is 0. Yeah, indeed. So instead of 1, just put another element. Oh no, wait, because that's not possible, because there are just 2 rows. Okay. So what I meant is, instead of the first batch, let's get second batch, second row. Great. You see now we get a different number than 0 and 1. Fantastic. So now that we just had a look, let's continue and actually have, because right now what we've done is just to define the handcrafted, say, weight for our filter. But what we want to do now is to compute the PyTorch weights and basically replace those by our handcrafted ones. Okay. How do we do that? So let's first define the ingredient and replace the PyTorch weights by our handcrafted weights. Okay, great. So let's do that. So orient gradients. So again, we're going to use our well-known conv2d. Okay, and as we know, the first element is going to refer to the input channels, because we're going to have 2, and in the output we're going to have 2 times the number of orientations. And again, here we're going to have the kernel size that we just want 1, so 1 by 1. So a very simple 1-1 mapping with a kernel of size 1, as simple as it can be. And then we're going to, well, there's no need to define it explicitly if we're going to place it equal to 1, but just to stress that the stride is going to be equal to 1. And the bias, we're going to set it equal to false, again, because throughout the practical you'll see that we'll be doing that. Okay, great. That is going to give us the gradient, but we specifically want to extract the weights. Okay, so we want to extract the weights of this layer. So to do that, what we can do is the following. We can do, actually, and let's put it explicitly here, string. So I'm going to say PyTorch weights. So just as we did for the handcrafted, let's just extract, say, the first row, and we extracted say, so first batch, or well, second batch, we start with one, so second batch, second row. Okay, we're gonna do that. And so how do we do that? Well, simply to the gradients, we're gonna extract the weights like that. Fantastic. And we just want to visualize the, say, second batch, second row of that batch. Great. So that we, in that way, okay, fantastic. Yeah, that is why. Okay. All right, so now let's have a look. Yeah, fantastic. So you can see how they actually are different. Okay, so this is the handcrafted version of the weight in that specific position, while the same position for the PyTorch weight is different. So what we want to do is get rid of this one and introduce the handcrafted one. Okay, great. So let's do just that. But what we need to ask ourselves first, because we always are tempted to just say, okay, so let's just equalize the oriented gradients. So let's just do oriented gradients weight, so the extracted weight from PyTorch, and equalize it to the one that we computed, right? So just say, okay, this is equal to orient, that's it, end of the problem. But we, before doing this, we need to verify that the shape of both are the same, otherwise this equation doesn't make sense, okay? Because they need to have the same dimension. So let's actually verify that. We can do that very simply, although we can already guess it, but actually let's visualize it explicitly. So if we print out the shape of the PyTorch one and we print out the one for the handcrafted, indeed we have the same shape. So this means that we can just say equalize them directly. Okay, but as we saw for the D, we could not do that because the shapes were not by default or automatically be given the same. So we needed to reshape and expand the original, or better say the handcrafted weight tensor. Okay, but in this case for orient there's no need, so perfect, that's great. Fantastic. So that is basically what we need to do for this particular say filter. But now let's continue and now let's have a look at another type of filter, and that is it's called bilinear spatial binding. Okay, so let's actually define that. So bilinear spatial binding, this BSB. So first of all, what is this? Okay, so BSB is a process used to aggregate, you can aggregate, or you can say as well group, to group information and in our case, when I say information, I mean gradients mostly, or gradients, or you can call it weights. Yeah. So the weights into small regions that we are going to call cells. Okay, so into small regions of an image that we are going to call cells. Okay, great. So how does this really work? Okay, well, let's find out, and we're going to do it just going through the code. Okay, so first of all, what we want to define is something called window. Okay, a window, and let me talk about that now. So we're going to have a window, and when I say window, what do I mean by that? Well, the window is a sequence of weights, okay? Sequence collection, okay, of weights. But it's not just like that, but weights arranged in a specific manner, okay? Okay, so the value of these weights, as we move from the center is going to be, or is going to better say, decrease. Alright, so basically what this is saying is, look, if I give you a sequence of weights, this window is going to be able to have the highest weights in the middle, and as we move away from the center, we're gonna have a decreasing, so we're gonna see how our weights decrease in a smooth way. Okay, all right, so essentially the message is the following. So the message is that the closer we are to the center, the higher the weight, and the farther we are, the smaller the weight. Great, that is the idea, very simple. Fantastic. So again, this is a different, say, handcrafted gradient. So in the sense that we're going to handcraft the weights again for this specific filter. Okay, just as we did with first D, with the gradient filter D, and what we just did now with orient. Okay, in a very similar way, complete analysis. Okay, great. So let's start with that. So let's create a sequence which is going to be stored in the tensor. Okay, so when I say sequence, I mean the values that are going to be embedded in the tensor. Okay, so, and this is going to be from 1 to the factor of 2 times the cell size. Okay, and why 2 times the cell size? Well, because we not only want to take into account the cell that we are, say, targeting, but we also want to take into account neighboring values. Okay, so that we have a smoother, say, transition from the center values, the center weight values, towards the exterior, right, the extreme weight values. Okay, fantastic. So let's do it now. Let's call that. So in this case, well, let's define this variable of cell size. Let's say equal to 4, just for example. And again, remember that the original code, we set 8, but don't worry because we're going to implement all this new code to the original function at the end of it, okay? Alright, so let's do that. So how do we create these tensors? So simply what we're going to do is torso tensor, and we're going to have a range, and remember we want both the 1 and the 2 times CS to be included, okay? So remember that for the second element in the range, in order to be included, we need to place a +1, okay? Okay, great. Fantastic. So now we have the sequence. Let's have a look. Let's have a look at the sequence. Great, you see we have a tensor, and in this tensor we have the sequence from 1 to 8, both included, of course. Okay. Now, once we have the sequence, what we want to do is to calculate the center of the sequence. Okay, and we'll see why we're doing this. So, calculate the center of the sequence. Okay, and once we do that, we're gonna then subtract it from the original sequence. And why are we doing this? Because this operation is going to result into basically shifting shifting the sequence in a way that it is going to be centered around 0. Okay, great, and that's exactly what we want, because remember that in the center we're going to have the highest value, so we want our sequence to be centered, so basically centered at or around 0. So yeah, to do that, let's apply what we just discussed. So torch.tensor, and what we're going to do is, okay, we're going to take this original range and subtract it, and we need to subtract the center. And what is the center? Well, the maximum value of the sequence, in this case, of course, 2 times CS plus 1 over 2. Okay. All right. Okay. Fantastic. So that is going to give us the operation. Let's see. Oh, what happened here? Unsupported operand. So we're saying that we cannot operate with range and float. Oh, okay, I see what is happening. So you see that I subtracted, but within all being the tensor. But no, this is not the case. What we want is just to have the tensor minus the middle. Exactly. That's what we want. Fantastic. So you see how now we have, say, our sequence centered around 0. This is 0. Fantastic. So we have at the left negative values, at the right positive values, but it's right in the middle as we want it. Fantastic. So let's continue. Let's continue analyzing. And the first thing we notice is this is not normalized. Okay. What we want are values that are between 0 and 1. Okay. And to do that, what we can do is just dividing by the cell size. Okay. So we simply take this operation right here, and we divide it by CS. Fantastic. You see how now we have all our values in between 0 and 1. Fantastic. Well, actually, not quite, right? Because I see negative values. So to be completely normalized, well, we need to have all positive values between 0 and 1, because now we have between -1 and 1, right? So now what we need to do is to take the absolute value to have range between 0 and 1. Okay, fantastic. So to do that, we simply take this. We're just going to take the absolute value of that operation. So torch.abs. Okay, let's have a look. Fantastic. You see how we just got the positive values. Well, but are we done? Not quite, because remember, our window needs to have, say, the greatest weight values in the center, okay? As we move away from the center, we expect the weights to decrease smoothly, yeah? So, well, this is not what's happening here. It's actually happening quite the reverse thing, right? So we have the lowest value in the middle, and as we move away from the middle, we see how they increase. So this needs to be modified. And how are we going to reverse this process? So essentially just doing 1 minus this value, right? Because think about it, if you take 1 and subtract 1 minus everything on this value, the values that are, and as all of them are between 0 and 1, as we subtract the external ones, which are the greatest in this case, are going to be the smallest when we do 1 minus that value, right? And so on. So now we are ready. Let's define the window. So the window then is going to be this list or this sequence of weight values, having the greatest at the middle and smoothly decreasing the weight values as we move away from center, right? Great. So we just do that. So 1 minus this operation right here. And let's have a look at it now. Oh yeah, that looks great. So you can see how now we have the reverse. You see, now we have the greatest values, and realize that we have the exact same information. We have the exact same information that before doing the 1 minus, just that now we rearranged it as the, say, definition, standard definition of window, okay, for this BSV method. Great. So now what is next? Well, we just defined the handcrafted weights for our say layer or gradient, yeah. But now it's time we define the actual gradient, right? And remember, these gradients, what they do is pulling. When I say pulling, I mean that we basically, or these gradients, what they do is to aggregate information, okay, over, in this case, a cell, specific region, basically enclosed by a cell, and say out of this region gives us a gradient associated to it, okay? But yeah, actually, let's write that down, it's important. So let's say here 3.6.2 the aggregated gradients, and we're gonna have the because we're gonna aggregate both in the horizontal and vertical directions independently, okay? Just as we've been doing with the say gradients, the gradient and the say the first gradient that we defined, right? So we're gonna call these gradients pull u, and pull V. Great. And of course with custom weights. Great. Fantastic. So pulling is a way to aggregate information over a specific region of the input. Okay. Basically, a cell of pixels in an image. Okay. Great. What this pooling does essentially is reducing, okay, the size of the data, and what I mean by that is that the spatial resolution is reduced, yeah, while retaining the fundamental or key gradient information. Okay, great. But yeah, let's proceed and define these gradients. Okay, let's do that. Fantastic. So we have number of orientations. Again, we stress that is equal to 9. And let's start with the horizontal pooling. Okay, so the horizontal pooling we're going to call or basically pull U, yep. And essentially again we are going to use the convolutional layer, come to deep, and again what is the structure? Well, is going to be, well, here this pooling is taking 2 times number of orientations, so it's taking basically all the possible gradient orientations. Okay, and as an output we're also going to have 2 times number of orientations, so again we have a one-to-one mapping, right? And what about the kernel? So the kernel is going to have the following shape. It's going to have one column, well, sorry, one row, and it's going to have 2 times CS. All right? And why is that? Well, remember, what we want is to say scan over as we go through. We scan over the cell. Yeah. In this case, say let's think about the example that we were talking about. The cell size is equal to 4, right? So if the cell size is equal to 4, imagine that we start by the top left. Okay, we start with the top left cell within that region. Yeah, with that within that 4x4 cell. So what's happening is, remember, the kernel is going to be placed in the middle, right? It's going to essentially overlap with this top left cell, and of course we're going to have essentially these cells to be overlapped, these kernel cells to be overlapped with the original cell, and we essentially are going to have those 4 covered, and we're going to have the other 4 that are going to be, say, outside the cell. And why we're doing this, because we want to take information from neighboring cells, not only from the selected cell. So it's the same reason that we mentioned above. Okay, great. So that's the kernel. But based on the selection of the kernel, how are we going to set the padding? Okay, so let's discuss that. Padding is going to be no padding in the rows. Okay, so we're not going to add padding in the rows, but we are going to add padding in the columns. But how much? So essentially, how much padding? So essentially, we're going to take that. We're going to have the cell size. Okay, and the reason is exactly the same why, for example, in the case, in the first grid that we defined. Yeah, remember for the color channel, find it here. Yeah, here exactly. So let's take this example. Okay, for this example, we had a padding of 0 and 1, given a kernel of 1 and 3. Why? Because here the kernel was moving in the horizontal direction. Okay, and had as dimensions 1 row, 3 columns. Yeah. So when it was placed in the top left position, yeah, the left, say, cell of the kernel was left outside the original cell, right? So this cell needs to be taking some kind of input, some kind of pixel input, even though it's not within the selected cell. So to actually make it take or give it an input, we needed to place a column of, in this case, zeros, because remember, if we don't specify what we place in the padding column, it's going to be a 0. So essentially what this is doing is taking or basically what we needed to do is to place one column extra at the left and other column at the right end of the cell size. Okay, so here is exactly the same reasoning, but instead of having just one, say, neighboring pixel in the left and another one in the right, now what we have is actually as neighbors CES neighbors, CS cell neighbors. Okay, so that is why we need to place essentially these value of CES over 2 neighbors, okay, because it's half of the CS. Yeah, great, that's brilliant. So now let's also discuss the stride. Okay, the stride, and the stride is going to be equal to the following. The stride is going to be 1. So that means that we are not going to skip any row. So as we move up and down, okay, the kernel will not skip any row. And that is exactly what we want, because we are scanning in the horizontal direction. So when we are done with certain row, we want to move to the following one without skipping it, right? So that makes sense. And how about the console CS? What does this mean? Well, this means that the kernel is going to skip CES pixels, that meaning one entire cell horizontally, okay, after each step, right? So why are we doing this? Well, because we want a partial overlap between neighboring regions. That is because essentially that's because each region is going to contribute information to the next one. All right, so basically ensuring that the transitions between cells are smooth. Okay, so it's the same reason that we mentioned above. We want this smooth transition between cell values containing weights. Okay, all right, so that explains perfectly why are we dealing with that stride in particular. Okay, again, bias, we're gonna set it to false, just as we've been doing. And what about the groups? What about the groups? Again, we want to be working with a one-to-one mapping. Okay, so if we want that, we need one channel per group. Hence, as we have 2 times NO input, 2 times NO output, we need NO groups. Well, 2 times NO groups, I mean, in order to have a one-to-one mapping. Makes sense, great. So that is basically the definition of the horizontal pooling gradient. But we actually, let's have a look at the, because what we are interested in is in extracting the weights that it contains, right? So in order to do that, as always, dot weight data. And hence, actually, let's have a look at the shapes of the weights, because we are going to need that. We're going to need that when it comes to the step that we already really acquainted with, that is getting rid of the PyTorch weight computations and replacing those by our handcrafted weight computations. Okay, great. So let's have a look at this. Oh, great. So you see we have a 4D vector again, and we're going to have this particular shape that we again need to replicate when the right time comes, right? Okay, so now before we move on and actually replace the, say, custom PyTorch weight values by the handcrafted ones, we need to do the analogous for the vertical pole, because remember, we are also defining the vertical pole. So pole V, great. So for that, well, it's completely analogous, right? But now instead of having a kernel of 1 row and 2 times CS columns, because we were scanning in the horizontal direction, now we need the opposite. We need 2 CS and 1, because we're gonna be scanning in the vertical. Okay, and completely analogously, we need here to have CS over 2, so basically rows and no columns. And for the stride, now what we don't want to skip are the columns, hence we reverse it. Great. So that is perfect. So now, well, just for sake of clarity, actually have a look. You see now the actual elements, because remember, these 8 elements, are the ones that are contained naturally by the handcrafted, well, I mean, of course, analogous. These are the weight values that PyTorch computed for us. Okay, but instead we want to replace those by the handcrafted ones that are stored in window. All right, great. So in order to do that, we proceed in the completely analogous way. Okay, so let's do it. Now let's compare. So compare the shapes. Let's compare the shapes. So to do that, actually print out, so let's say the shapes of our handcrafted weights, okay, are going to be the following. Going to be window, the shape. Indeed, as we expect, we have 8 elements within the window tensor. But again, this, you see, this is a 1D tensor, so you can already guess that we are going to probably need to reshape it. We're going to probably need to reshape it when it comes to equalizing the weights computed by PyTorch and these. Okay, but yeah, makes sense. Something we have encountered before. So now that is about the shapes of the handcrafted weights. So how about the shapes of our horizontal pulling weights, so the custom ones? Yeah. So actually, let's print that out. So the shapes of our PyTorch, in this case PyTorch, or PyTorch horizontal pulling weights. Okay, and well, essentially that is exactly this, exactly what we computed in here. Great. And let's have a look. You see, so by default, the shape of the as we saw above, of course, is going to be 18.118, while the handcrafted one is 8. So definitely it's going to need manipulation. Okay, that's reshaping and expanding. And don't forget that we're not only dealing with the horizontal pulling weights, but we're also dealing with the vertical one. So we need to specify that. So we're going to need vertical here. Yeah, and V. Indeed, we're going to get, you see, now the weights are stored in the rows, not in the columns. Okay, so great. So now let's continue because now what we need to do is to reshape this. Okay, so let's go step by step because we're learning, right? So let's first convert window, so the window tensor, into a 4D tensor, because as you saw, it is right now is a 1D tensor. Makes sense? So 4D tensor okay. All right, so and let's print that out. So window dot, well, we need to reshape it to what? Okay, so let's have a look. What we want is to move our elements to the, well, and actually wait a second, because we need to do one for the horizontal and another one for the vertical. So for the horizontal pulling weights. Okay, so basically reshaping, let's put here reshaping, and yeah, reshaping horizontal pulling weight. So we would have, well, for the horizontal we want to pull 8 to the last dimension slot. So, and we, for now, because we're just reshaping, we just want to say expand the dimension from 1 to 4. So let's just place here once, just like we did before, so that we go from 1D to 4D. And in the last position, what we want is just the original. We want the original dimension, because it's where our information is still going to be located, right? So like this. And this is going to give us the reshaped horizontal pulling weight tensor, right? Great. So now let's actually see the shape. Let's see the shape of this. Shape. Great. So you can see that indeed we get the 1118. We indeed went from the 8 original dimension of the handcrafted weight tensor to this 4-dimensional tensor with the information that was originally stored in the handcrafted 1D tensor still there. Okay, so it's there. Great. So now we need to do the same for the vertical. Okay, for the vertical. So vertical. And watch out here, because now what we want is this is to reach this say shape. Yeah. So again, we're gonna need a 1 here. We're gonna need a 1 here. But yeah, careful here, because now we want to have the original placed in this position, because it's where we found out that the original elements need to be placed in. So the -1 is going to be this, and essentially this is going to be 1. No -1, because if I do -1, I'm going to get an 8 there. So -1 like that, perfect. And now let's print the shape, which is going to, of course, be the same here, that above. And let's have a look. Fantastic. So you see explicitly that, first of all, we went from the original 1D handcrafted weight tensor to this 4D. And actually, let's actually, instead of seeing the shape, let's actually see the value so that you can explicitly see that we have the same values. Exactly. You see, 1D tensor with 8 elements stored in it, right? And we went from that to a 4D tensor with the same elements stored in it, right? That's for a horizontal pulling. Yeah, that's what we need to do for horizontal pulling. And remember, we're not done yet, because right now this tensor has shape 1118, and what we want is 18118. Yeah. So we still need to do some operations on that. Great. But that's regarding the horizontal pulling weights. How about the vertical? So again, we start from the original weight handcrafted tensor, and we need to go from this one to 18181. Yeah. So now, indeed, we're gonna have our values, instead of being stored as columns, as it was done for the, say, reshaping of the horizontal pulling weights. Now we're going to have our values, our weights, are going to be stored in the vertical direction, that is basically stored in rows. Okay, and indeed we get the 1181. So that's exactly what we want. Okay, great. But we are not done, because neither for the say 1118, as remember we're going to need here to have an 18, and same story for the vertical pulling. Yeah. So to do that, well, what we need to do is just to expand. We need to expand both. So let's proceed. So actually, now we are going to get the explicit horizontal handcrafted pulling weights, because now we're going to expand them and we're going to get the shape that we want, the final one. So okay, let's print the result, and what we're going to have is, so we end up with the horizontal shape that we want. So why? Because essentially we're going to get this and put it in here. Yeah. And now what we need to do is to expand to what? So remember, expanding just makes copies in of the element that we indicate, and as many as we indicate, right? So we want to actually have 2 times number of orientation copies. Why? Because remember, the shape that we want is 18, and 18 comes because number of orientations 9 times 2. So 2 times number of orientations. That is the first dimension that we want. And what about the rest? So essentially for the rest, we already have them as we want. For now, we're focused on the horizontal, right? We're focused on the horizontal. So let's let's put here horizontal instead of this. So horizontal handcrafted pulling weight shape. Okay, we're gonna have this one, and the rest is not gonna change. So let's just place -1 because, as I said, doesn't change. Right. And again, let's place here a clone because, and we don't want to modify the original window, say handcrafted values. We're just going to copy an independent copy. Okay, so write this properly. Print. Great. Fantastic. So you see how we get all. You see, these are the original. These are the original handcrafted weights in every single row. Okay, that's exactly what we want for the horizontal. Okay, fantastic. And we have 18, of course, because that is essentially the shape that we are aiming for. Yeah, these 18 repetitions. Okay, great. But actually, let's visualize shape to confirm that definitely we have 18. Fantastic. You see, we have exactly the shape that we want. And remember, why are we doing this? Because we want to replace. We want to replace the custom PyTorch values by the actual handcrafted ones. Yeah, that's the goal. And to do that, we need to first match the shapes and then equalize. Great. So that's for the horizontal. And for the vertical, we need to do the complete analogous. So we would have vertical here. Vertical handcrafted pulling weights. And essentially now, what's the difference? Well, the difference is that now what we want to keep is the actual number prior to the columns. Okay, the rows. Okay, so well, this is horizontal. Watch out, exactly. So -1 in here, fantastic. And what else? So now we need to modify the expand. So the expand, and what happens with expand? Well, actually, given that we already modified the shape, yeah, the expand looks exactly the same way. So yeah, that is already correct. So now let's actually verify that. Fantastic. So you see, we exactly get the shape that we wanted. That was the goal for the vertical. Let's put here vertical. Okay, so for the vertical, we wanted 18,181, and for the horizontal, we want 18,118. Fantastic. So now, what is left to do? What is left to do is to customize our pulling weights. Okay, so essentially, get rid of the PyTorch, get rid of the weights that PyTorch computed for us, and input our handcrafted weights. Yeah. So as we've been doing for the last gradients. Okay. So customize pulling weights. Fantastic. Great. So here, pull. Well, remember the custom. So the wait a second. Customize. Yeah. So the ones computed by PyTorch are this. So weight data, and what we want is to replace those by the ones that we just obtained, right? So for the horizontal ones, yeah, what we need to do is just copy paste this. without the shape, of course. Great. In that way, we simply get the the weights completely customized. And now the complete analysis for the vertical pulling weights. Okay, but instead of having the last value here, we have it in the rows, and that's it essentially. Okay, fantastic. In that way, we already have, because actually let's verify that. So if we visualize now, the because I want to compare the ones that were computed by PyTorch and the ones that were computed by our handcrafted formula. Okay, this was done above. So you see here I extracted them, but I didn't say visualize them. There's a lot, so let's just visualize actually the ones in the 0, 0. Yeah. Okay, and same for this. Okay, great. You see how they are different. They are completely different, yeah, to the ones that we have. Yeah, these are the ones that are computed by PyTorch. So for the horizontal pulling, we have minus 2355 blah blah blah, and if we compare it to the horizontal that we have for the handcrafted, yeah, this one 1250 blah blah blah. So you see how they are different. And for the vertical, same story. For the vertical, same story. Because of course in our case we have the same for the vertical. So indeed they differ as well from the ones that we handcrafted, that we got in a handcrafted way. Okay, great. But now if we visualize, of course, let's just visualize still. Indeed, we get, so essentially, the ones that we want. We indeed get, for both of them, the content, the weights that we obtained in a handcrafted way. But yeah, that is all for this video. I hope it is helpful, and I am willing to see you very soon.